Hello, and welcome to this introduction to AWS F1 and the SDAccel development environment. This module is part of an online training series providing practical instructions on how to develop accelerated applications on Amazon F1 using the Xilinx SDAccel development tool flow. We will start this presentation with a high-level overview of the F1 Cloud Compute instance and the SDAccel tool flow. We will then provide a description of the F1 hardware and software stacks and explain how hardware acceleration works on the F1. With that foundation established, we will provide an overview of the steps involved in creating acceleration kernels, compiling the FPGA design, and creating the Amazon FPGA image, or AFI. Lastly, we will describe the steps and tasks involved in developing a host application accelerated on the F1 FPGA. This introductory module is aimed at providing a global comprehension of the F1 development process. Each of the topics covered in this module will be expanded upon and covered in detail in subsequent training modules. But first things first. Amazon F1 is an elastic cloud compute instance combining x86 CPUs and Xilinx FPGAs to create and run accelerated applications. The FPGA serves as a high-performance acceleration compute resource to the x86 CPU. F1 instance comes preloaded with all the necessary development tools to create, optimize, and program the FPGAs. Once the desired FPGA program is ready, it can be deployed in a few clicks on any number of FPGA instances, providing elastic compute acceleration in the Amazon cloud. There are obviously many benefits to the F1 platform. Here are just a few. F1 makes FPGA acceleration available to a larger community of developers who would not otherwise have the resources to create their own acceleration architecture. Like F1 makes FPGA acceleration available to millions of potential end users who will be able to tap into a broad marketplace of acceleration-ready apps. F1 instances come with one or more high-end FPGAs, each providing vast amount of programmable logic. This allows creating massively parallel FPGA accelerators, delivering orders of magnitude increases in application performance and throughput. Programming FPGAs requires dedicated tools, compilers, and debuggers. Amazon simplifies the development process by providing cloud-based FPGA development tools, effectively democratizing the FPGA programming process. Many applications are ideally suited for the FPGA-based acceleration. Genomics, big data, and financial analytics, security, video, machine learning are all important and prominent examples. But any compute-intensive application benefiting from the massive parallelism and deep pipelining is a prime candidate for F1. This is because at the heart of F1 hardware platform, you will find the Xilinx VU9P FPGA. Xilinx FPGAs come with a vast amount of dedicated programmable logic. Unlike CPUs and GPUs, which have predefined execution units, Xilinx FPGAs can be programmed to have any number of task-optimized execution units, or kernels. The Xilinx VU9P FPGA is a high-density device fabricated in 16-nanometer process. A single VU9P provides over 2.5 million logic cells, more than 6,800 DSPs, and 4 DDR4 channels providing a total bandwidth of 48 gigabits per second. With these specifications, the VU9P allows for massive I/O transfers and massive parallelism and is ideal for accelerating compute-intensive applications. When it comes to instance configurations, AWS provides two options: an instance with one FPGA and another with 8 FPGAs. This provides great flexibility to application developers and ensures no one will run the risk of running out of FPGA logic. Now that we have covered the basics of the F1 platform, let's take a look at the F1 development process. Because F1 is a cloud compute instance, development can also happen in the cloud. Developers start by logging into AWS and then select an instance loaded with the FPGA Developer AMI and Hardware Development Kit. AMI, which stands for Amazon Machine Image, it designates the initial configuration installed on the selected machine. In this case, the FPGA Developer AMI provides all the necessary tools to develop the FPGA program on the selected cloud instance. The Hardware Development Kit provides the scripts and files necessary to target the F1 platform. The developer can then use these tools to design, debug, and optimize both the FPGA program and the host application in the cloud. Once the final app is ready, it can be published on the AWS Marketplace as a new AMI. But it is important to know that development on the cloud is not the only option. Amazon also makes it possible to develop on-premise, that is, in your own environment. All the tools and files needed to develop on F1 can be downloaded and installed locally on your own machines. The development process in the cloud or on-premise is strictly identical. Once you have completed the development of the FPGA program and of the host application in your environment, you can upload both the binaries to the cloud, execute on F1, and publish your app on the marketplace. Now let's talk a little bit more about the development tools. Every compute platform needs a tool chain. SDAccel is the development environment for F1. As we've established, F1 is a compute instance combining an x86 CPU with the Xilinx FPGA. SDAccel provides all the necessary tools to develop, compile, debug, profile, and execute the accelerated application running on F1. The host-side application, here shown on the left-hand side, is developed using standard C or C++. The FPGA, shown on the right-hand side, can be programmed using traditional RTL code, but also using C, C++, or OpenCL. This flexibility is key to enabling a wide community on F1. With the RTL flow, SDAccel allows existing RTL designers to capitalize on their skills, reuse their IP, and leverage them in the cloud with minimal effort. With the C and OpenCL flow, SDAccel opens FPGA programming to software and algorithm developers. SDAccel is a fully integrated Eclipse-based environment. It provides all the necessary features to develop, profile, and deploy applications accelerated using Xilinx FPGAs. Using SDAccel, developers can concurrently develop the host application and the FPGA kernels and execute the two together when ready. The tool offers different testing and execution models, providing various levels of debug visibility. In addition, SDAccel provides comprehensive profiling and performance analysis tools, which can be used through the development and testing process. These features are very important to help developers tune their applications. By watching all of the modules of this self-paced training series, you will learn in more detail how to use SDAccel and its features to create accelerated apps for Amazon F1. For now, we'll take a closer look at the hardware and software stacks of the AWS F1 platform and explain how they work together to provide an acceleration solution. The primary motivation for running on F1 is to accelerate CPU-intensive and performance-sensitive applications and workloads. On F1, acceleration works by offering compute-intensive and deeply pipelined parts of your application to the FPGA, where customized hardware accelerators provide the needed performance boost. The rest of the application executes normally on the x86 CPU host. Communication between the CPU and the FPGA is carried over the PCIe interface. In the next few slides, we'll look in more details at how that communication from the CPU to the FPGA and back actually works. Here's an abstracted model of the AWS F1 platform. On the left-hand side, in the gray box, we have the software stack running on the x86 CPU. On the right-hand side, in the red box, we have the hardware components in the FPGA. On the host CPU, the custom application interacts with the FPGA using the OpenCL API. OpenCL is an industry standard providing clear semantics to parallel computing. The OpenCL runtime is responsible for managing and servicing the various acceleration requests sent to the FPGA. At the lowest level, the drivers handle the PCIe transfers between the two devices. The FPGA sits on the receiving end of these PCIe transactions. The F1 FPGA comes preloaded with the necessary logic to DMA the data into local DDR memory. The custom acceleration kernels can then read this data, process it, and write it back to DDR using standard AXI4 interfaces. F1 exposes clear and standard interfaces for the app developer. Everything below the red line shown here comes off the shelf with the F1 platform. Everything above the line, host code and hardware kernels, is provided by the developer of the accelerated application. Amazon and Xilinx have tightly collaborated to make this platform as performant, robust, and easy to use as possible. By using standard OpenCL and AXI interfaces, F1 hides the complexity involved in building a heterogeneous platform and lets developers focus on what matters most to them, accelerating their code. Speaking of accelerated applications, here's an abstract example of how one may look. In this example, we are looking at an HEVC video encoding app. HEVC, also known as H.265, offers an average bitrate reduction of 62% for 1080p frames compared to H.264. With the advent of online video streaming, high-efficiency video codecs such as HEVC are in high demand. Unfortunately, HEVC encoding is a compute-intensive task, and neither CPUs nor GPUs offer enough horsepower to do this. Here's where the F1 comes in. The Xilinx FPGA is an ideal platform for video acceleration. Custom data paths can be created to parallelize and pipeline the video encoding process. On the x86, the app developer can create a custom FFmpeg plugin, which will offload the HEVC encoding requests to the FPGA. Creating acceleration plugins for widely used programs and frameworks such as FFmpeg is a very powerful proposition. With this approach, end users can keep working with the program and the tools they use every day and have F1 accelerate their jobs transparently. As mentioned previously, the F1 FPGA comes pre-configured with hardware functionality to manage communication to and from the FPGA. This hardware layer is commonly referred to as the F1 shell. The shell is a key component of the F1 platform and will be very often referred to throughout this training series. The shell abstracts the FPGA IOs and presents a standard AXI interface to the kernels. The shell also includes features ensuring the reliability of the platform and security of the hardware IP. The shell has been thoroughly tested and has been designed for optimal performance. Another central concept in the F1 flow is the Amazon FPGA image, or AFI. The AFI designates the program running on the FPGA. It is effectively an image of what is in the Amazon FPGA. Since a lot of proprietary IP is likely to go into the FPGA, and therefore in the AFI, Amazon provides a highly secured mechanism to manage and access these files. All AFIs are encrypted, and the F1 system works in such a way that end users of the application never have direct access to them. Ultimately, AFIs can be associated with AMIs, or Amazon Machine Image, and offered on the AWS Marketplace, allowing developers to monetize their acceleration IPs. Later in this training series, dedicated modules will cover the full details of kernel development and AFI creation. So after this look at the hardware components, let's now review the host application execution stack. As mentioned earlier, the stack is based on OpenCL, an industry standard for parallel computing maintained by the Kernels group. OpenCL follows a master-slave model which cleanly separates the application code from the kernel logic. Using the OpenCL API, the host application transfers data and submits tasks to the acceleration logic in the FPGA. The OpenCL runtime dynamically schedules and orchestrates the communication between the host and the FPGA. There are many benefits to using OpenCL, starting with the fact that it has been designed specifically for heterogeneous computing, which is exactly what F1 is about. OpenCL has been designed to be platform independent, which makes the code portable across CPUs, GPUs, and obviously FPGAs. Because it is open and standard, you will easily find a lot of learning resources online. If you're not already familiar with OpenCL, a simple Google search will result in many links to primers, trainings, and examples. Another key advantage of OpenCL is its runtime. The runtime manages all of the communication between host and the device and takes away the bulk of the complexity of optimizing parallel computing apps, delivering fast time to results. Lastly, a very nice feature of OpenCL is the ability to dynamically swap and load different kernels. This means that on F1, your application can start using the FPGA to accelerate a particular workload and on the fly, load a new AFI to accelerate a new type of workload. For all these reasons, OpenCL is a natural choice for F1 platform. You'll be able to learn more about the OpenCL API later in this training series. To summarize what we have covered so far, the FPGA program is compiled, encrypted, and registered as an AFI. The host application, for example, a framework plugin, interacts with the FPGA using OpenCL. Once you have the two working together, you're ready to create and publish your own AMI. This will allow end users to start their own F1 instance loaded with your AMI and have instant access to your acceleration app. Amazon provides various pricing models, offers great flexibility, and a rapid path to monetization. Let's now discuss the steps required to create FPGA kernels, assemble the FPGA program, and compile the AFI. The AFI creation flow can be decomposed in three major steps. First, the kernel creation phase. Here you'll be using SDAccel to create kernels from either C, C++, OpenCL, or RTL models. Next, you'll be compiling the platform. Here, the SDAccel compiler is used to link together the previously created kernels with other required hardware components and generate the FPGA binary. In the third and final step, a special AWS service is used to create, encrypt, and register the AFI. We'll now look at these three steps in closer detail. As just mentioned, kernels can be created from either C, OpenCL, or RTL code. Let's start by discussing the RTL flow first. This flow caters to existing RTL designers and allows them to reuse existing RTL code as F1 accelerators. To be used on F1, existing RTL code must be packaged as SDAccel compliant kernels. This primarily means complying with specific interface requirements. This training series includes a module focused on RTL kernel packaging process and provides all the necessary details on interface requirements. For best results, it's recommended to design RTL kernels with F1 specs and the app performance goals in mind. To facilitate the RTL kernel design and packaging process, SDAccel features a special wizard guiding the user throughout the interface definition steps. The output of the packaging flow is an XO file. This is a container file which includes all the information needed by SDAccel to use the kernel. Just like C code can be compiled in .o object files and which are later linked to produce the final executable, kernels can be packaged as .xo files which are later linked to produce the FPGA design. The XO files are effectively the key building blocks used by SDAccel to assemble the FPGA design. Kernels can also be created from C, C++, or OpenCL code. This flow is well suited to software and algorithm developers. It makes it easier to start from an existing C or C++ application and accelerate the portions of it. SDAccel provides a special parallelizing compiler which synthesizes high-performance kernels from C, C++, or OpenCL. The SDAccel compiler is able to extract parallelism from loop structures and has built-in optimization tuned for Xilinx FPGAs. A good analogy is to think of it as a cross-compiler targeting a special type of architecture. The output of the cross-compiler is a kernel package or an XO file. The SDAccel compiler supports a rich set of C, C++, and OpenCL constructs. When it comes to OpenCL, the compiler specifically supports OpenCL 1.0 embedded profile, OpenCL 2.0 pipes, and OpenCL 2.0 image objects. Kernels can be expressed with n-dimensional ranges, and the very convenient vector types can be used for SIMD optimizations. The code on the right-hand side shows a simple OpenCL matrix multiplication example. More than 80 examples of synthesizable C, C++, and OpenCL can be found on the SDAccel GitHub repository. These examples are a great way of getting familiarized with how writing good code for FPGA acceleration. After the kernels are created and packaged as XO files, the next step is to assemble the FPGA design. Remember that the kernels and the XO files are just building blocks. They need to be integrated with other hardware components such as the F1 shell. In this phase, the SDAccel compiler reads in all the XO files and automatically instantiates the kernels in the F1 shell. It then automatically generates the DDR interfaces and creates AXI interconnect logic. Finally, the compiler makes all the necessary wiring and connections. This results in a completely assembled FPGA design. After that, SDAccel runs the FPGA implementation flow. This is known as synthesis, placement, and routing. The result is an FPGA binary in the form of an XCL bin file. It's important to keep in mind that multiple iterations might be needed here to converge on an optimal design. The Xilinx ultra-fast design methodology guides are a very useful set of documents for achieving best results. The final step is to create the special AFI, or Amazon FPGA image. Here, the XCL bin is converted to an encrypted AFI using special AWS service. The resulting AFI is securely stored by an AWS backend service. The AFI can be identified and accessed using a unique AFI ID. This ID is written in the output AWS XCL bin file. In the diagram, this is shown at the bottom as the orange cylinder. The AWS XCL bin is what gets shared by app developers and app end users. It only contains the AFI ID. All sensitive FPGA design IP is securely stored. With the AFI ready, you're now ready to turn your attention to the host application. In this last part of this training module, we'll look at how to develop, execute, and test an application F1. The development of the host application can be broken down into 3 steps. In the development phase, you'll be adding OpenCL calls where necessary to interact with the FPGA. Then you'll compile and execute the application with the FPGA kernels. And finally, you'll use the SDAccel analysis tools to profile and optimize your code. The host application is written in C or C++ and is compiled with GCC. This process will be familiar to many programmers. What distinguishes an F1 app from a standalone program is the use of OpenCL to interact with the attached FPGA device. At a high level, there are 3 main things that the developer needs to think about. 1. Setting up the FPGA. 2. Passing data to the FPGA and executing kernels. And 3. Releasing the FPGA when the program returns. OpenCL provides the necessary API to do all of these things. There are, of course, various optimization considerations. These will be covered in other training modules. One thing to note is that the host application can ultimately take many forms. It can be a standalone executable, a plugin, or shared library, as we discussed in our FFmpeg example. It can be architected as a client-server system where multiple clients would submit acceleration requests to the server. There are truly many possibilities, and certainly one for every need. As we just saw, the host application is responsible for setting up the FPGA. When the application runs, it starts by loading the AFI ID from the AWS XCL bin file. It then contacts the AWS storage with the ID, which then downloads the proper AFI into the FPGA. The platform is now configured and ready to go. This setup step can repeat multiple times during execution. This will result in the application dynamically swapping and replacing AFI during runtime, a potentially very useful capability. Executing the application with the actual FPGA is obviously the end goal. But it is good to know that SDAccel provides 3 different execution modes serving different testing needs. Besides the hardware execution mode, where you run with the actual FPGA device, there are 2 other modes where the FPGA is actually abstracted and virtualized. In the first mode, which is the CPU emulation mode, the application runs with the C or OpenCL version of the kernels. This makes for very short and very convenient iterations. You'll want to run in this mode to confirm the functional correctness of the system. The second emulation mode is the hardware emulation mode. Here the application runs with an RTL simulation of the kernels. Because this mode relies on RTL simulation, it is the slowest. But it's great to test the host kernel integration, get performance estimates, and debug insight. Regardless of which execution mode you're using, you'll be using the SDAccel debug and analysis tools to inspect, assess, and profile your system. The tool lets you visualize many things, such as host and device events, OpenCL API call sequences, kernel execution sequence, FPGA AXI transactions, kernel start and stop signals, and many more. In addition, report files such as the very convenient profile rule checks highlight performance issues and provide improvement recommendations. These tools provide valuable insights and will help you get from an initial functional app to an optimized and high-performance one. We have completed our overview of the key steps of AFI creation and application development, and it's time to conclude this training module. To summarize, Amazon EC2 F1 is a compute instance with FPGAs that you can program and create custom hardware accelerations for your application. SDAccel is the development environment that will help you compile, debug, and deploy your accelerated app. You can then easily put your accelerated app on the AWS Marketplace offering a rapid path to monetization. You can find more information about F1 and SDAccel online, on the AWS website, on GitHub, and of course on the Xilinx.com website. This concludes this Introduction to AWS F1 and the SDAccel Development Environment module. We encourage you to watch the other modules in this training series to learn in greater detail about the platform and the development process. Thank you for watching.